We've been talking about quantum computing for about 65 years, and it's a journey riddled with setbacks. But now there seems to be renewed optimism, even capital, that we're getting somewhere. Are we? Raj, let's start with you. How much closer are we to having a quantum computer?
Well, it's great to be here, and thanks for that startup question. The question is a little bit misplaced because we have a quantum computer. It is being used for real work. The real work is defining exactly the use cases and how to approach those use cases in the near future. So the basic question is, quantum computers are no longer on benches and science benches and in labs.
But it's not a quantum computer that we envision to solve existential problems.
We believe we are within 2 to 3 years max of being able to solve large-scale problems, not just of theoretical interest and PhD generating theses, but things like how do you get to generative chemistry and go modify molecules to affect catalysis events in fertilizer generation. That's a $70 billion business. And if you make a 2% change in the time to solution, that's billions of dollars.
How close are we, Michael?
It's funny, without coordination, we have exactly the same number, 2 to 3 years. But
what's different this time around? Why 2 to 3 years?
There's nothing different this time around. Maybe the only thing that's different has been the attention span of people from the outside who jumped from quantum computing to blockchain to AI, and now are looking for something else because AI isn't panning out the way they originally anticipated either. Meanwhile, in the background, the people doing the hard yards have been on this continual, up and to the right trajectory. The machines get bigger every year, and I'll emphasize, these machines exist. You can run quantum programs on quantum computers and get real useful answers out. Now, the trick is, they're still a little small. They're a little bit too small to beat the best supercomputer, but we're legitimately talking about comparing today's quantum computers to the world's biggest supercomputers. That's the kind of comparison we make. And it's this next couple of years as the machines get bigger and then we help them get better from our technology, that we actually cross this threshold. And you as a user say, no, I'm going to choose the quantum solution instead.
You talk about it when the machines get bigger. Right now, just to put it out there, that quantum computer looks like the size of a fridge. Is that right?
So yes, but I think, so when I say bigger, I don't mean
more powerful?
All the infrastructure.
Okay, let's talk about that. Right now it is, what, 100 qubits?
Yeah, so a qubit is the information carrier, right? You should think of a qubit like a quantum transistor in a sense. But you can't just compare how many qubits to how many transistors, right? You have 10 billion transistors on a chip these days. You can't say, well, you've only got 100. It's about what that enables, what problems that enables. Now, 100 qubits, the kind of state-of-the-art average across the community, is still a little bit on the small side to deliver that advantage that we're looking for. But we think advantage only comes with around 900 to 1,000. So this is not infinitely far away. This is on the roadmaps of various teams in the next couple of years.
And Michael, I think the key thing is just not how many qubits you have, but how usable they are. Mm-hmm. In classical computing, that's like saying, I give you more cores, but the cores are deterministic. If I said, I give you more cores, but they're likely to fail more often, you might have a different view of how many cores you need versus usable cores you need. Our view is it's not a race to qubits, it's a race to the fidelities that are achieved so that you can trust the computation that you just did. And time to solution, because what quantum computing is generally you're running probabilistic problems, you throw it at it several times and you observe what the output is, or you throw it once and observe what the output is in a probabilistic sense. And time, the economic value is how long did it take to get the right answer for me? And that is not affected by just qubits. It's affected by how useful, how resilient, and how fault tolerant those qubits are.
So can I double click on that for a second? It may be a surprise if you're not an expert who spends your days looking at quantum computing. Quantum computers are very fragile. So when Raj is talking about fidelities and fault tolerance, He's really addressing the fact that a classical computer, the one in your laptop or your mobile phone, that can actually run for about 1 billion years. I'm not joking. It can run continuously for about 1 billion years and never be expected to suffer a hardware fault. A 1 turns into a 0. If it fails, it's because of software. In quantum computers, community average, it's more like 1/1000th of a second. That's about the average. So we have a lot of work to do to make the machines more stable. And this is where almost all the R&D comes in. That's what my company, Q-Control, focuses on, stabilizing the quantum computers so we can solve bigger problems.
So where are we with that?
It's happening right now, right? There are amazing results that are coming out all the time, solving real problems, where in the case of the commercial engagements we have with, say, IBM, our software is the difference between the quantum computer being no different than a random number generator, actually choosing randomly, or actually giving you the correct answer 100% of the time on a logistics problem that is relevant to scheduling and routing and all sorts of industries. So real problems.
I agree with you, Michael, that it's a combination of hardware and getting better and smarter and smarter software that will lead to these very large-scale systems. We're focused on both because the better the hardware is to begin with, the easier it is to get the correction done with lower kind of pain or overhead or tax, if you believe. We see machines today. We have 2 generations of machines now, which are being used by very leading market-making companies in different end markets, running real problems. Airbus and BMW, looking at solid fuels and the next generation of chemistry that is going to be required at chemical accuracies to figure out what the chemical reactions are in these going to be. So someday we get a 1,000,000-mile battery.
We talk about how, well, you talked about how there's already a quantum computer and that's solving problems. When it comes to qubits, we're looking at 100. Some say 10,000 is quite a critical number. Others say we actually need to get to 1 million. Give me a sense of what 10,000 allows you to do, what 1 million allows you to do.
So I'll say the answer is actually it depends on what problem you're trying to solve. There's nothing that says you have 1 million qubits and you've achieved the nirvana of quantum computing.
We talk about wanting to solve existential problems.
Yeah, but let's take one around, if you're doing supply chain, large-scale optimization problems. What you need are good, solid, somewhere between 50 and 100 logical qubits, right? Again, the scale of the problem. Training AI models, 100+ logical qubits. This is where, when I said logical, it's what Michael just said. These are the qubits you trust. So they've been error-corrected. And what we believe is the people who build, like us, the best-in-class physical qubits, apply error correction on top. You get to, if your ratio of physical to logical is 10-to-1 versus 1,000 to 1, you can get there in the next year or 2 with 500 qubits, giving you 10 logical qubits that you can use.
So sometimes our discussion gets taken away by the fantasy side of what you can do with quantum computers because it sounds so exotic. But in practice, you can actually solve important, less sexy problems that actually make the world go round. So we did a bit of work with the Australian Army. And the Australian Army works with the US military, and they do a joint military exercise that involves moving materiel on surface streets from all these different depots to the location of this exercise. It's called Talisman Sabre. That's a problem that is, there are commercial solvers out there. The Australian team will not use any commercial software because they don't trust that the results will meet their risk tolerance. So they literally have staff sergeants with pen and paper and with spreadsheets solving this problem. The issue here is that that problem is amenable to quantum computers and it is underserved by conventional technologies. So if a quantum computer can give a better answer, even if you can't prove it with a math proof, if you can show me instead of telling me that it's better, then that's a real win in areas that matter, in national security, in industrial logistics, in oil field management. In all of these different industries, that threshold of when you win is close and the advantages are extreme.
Before I follow up on that question, that answer. You talked about how it's clouded by fantasy. What's fantasy? What won't quantum computing be able to do?
Quantum computing is not magic pudding, right? There's an Australianism about the magic pudding that you keep eating it, it's delicious, and no matter how much you eat, it's still there. It doesn't solve everything. It doesn't fix everything. It doesn't replace all computers. It is a totally new kind of computer that complements what we already have. Just like GPUs complement CPUs. And we've seen NVIDIA become a $3 trillion company based on this admittedly niche technology that they totally dominate in the market. Quantum computers, in my view, I don't know, Raj may have a different view, look to be similar, that there'll be a specialized accelerator, but they provide the computational grunt that solves the real hard problems. So the fantasy comes in the narratives that they just fix everything, that problems are no longer hard. That's not true. There are still hard problems, but quantum computers can help address them, just like GPUs helped unlock AI.
Raj?
I agree. It's a hybrid infrastructure where classical and quantum are going to be used, but I want to be very clear that the quantum portion is not just about creating a faster computer to do classical methods. Quantum gives us the ability to look at physical interactions in a way, and then from that create new physical things that you couldn't have done before. Quantum computing allows you to model, for instance, carbon dioxide molecule, to then create a material that will absorb it very effectively for carbon sequestration and sustainability problems that you couldn't have done with any other tool. So I agree with you that there's a kind of feeling that quantum is just the faster computer, the fastest supercomputer that will solve everything. What it is, its beauty is, of course, it'll do some problems more effectively than classical computing, but it will allow us to do things that classical computers have never been able to do. And that is the beauty of creating more nature, right? New molecules, billions of dollars from personalized medicine, from personalized fuels and fertilizers. You never go out and get a prescription for a painkiller or an antibiotic. It generates the specific medicine for you because it understands the chemistry, your body chemistry and its interaction with drugs.
Michael says, show, don't tell, it's hard to prove, correct? But therein lies the problem for investors. They want proof, and how do you convince them? How should they be looking at it? Because obviously, you need a lot of funding for this to get to $1 million and beyond.
It's a roadmap. It's not for every investor. I'll be upfront. It's for those that see large markets like generative chemistry, which is, in our estimation, north of $1 trillion market, if you look at all the end markets being served, from pharmaceuticals to chemicals in it. And then look at the milestones that say, is the technology achieving the promise that is required to get to those markets, and are those tipping points in the markets forming? That's what we are seeing today in many of these end markets, right? When we say we need X amount of a size of a machine, if you will, capacity, it's not a Big Bang theory, right? That when you get to that, you suddenly have something. You can show things, you can show steps along the way that are provable, demonstrable, and they are in line with solving the larger scale problem. You solve problems at different scales. So confidence building in the technology in the context of a massive market, which will be disrupted by this approach, is absolutely possible today, and we are doing it. We just closed a very significant funding round with exactly those kinds of demonstrations of key market makers on large-scale use case problems, and the progress we've been able to make from going to a dream to demonstrating solutions at lower scale.
I mean, I agree with this. I mean, the first thing is that the technology is showing consistent, very substantial gains year on year. Whether that meets the timeline that a particular investor expects for their fund, for their thesis, that's a different question. I think of it this way. Would you in the audience, maybe some of you were quite prescient, but would you, looking back, had you not been so clever, would you have really loved to be in OpenAI and NVIDIA 6 months before everything blew up, 6 months before AI hit? You would be, if you're not already a billionaire, you would be a billionaire today. And that kind of opportunity, it can come if you're willing to weather the long path. NVIDIA is a 20, 30-year overnight success, right? They needed people behind them, and obviously the public market after a while, to support them as they continue to develop their technology and grow the market. I think the same is true in our sector. If you want the outsized rewards, if you want to be on the right side, the early side of the next OpenAI, the quantum version, then it means that your investment thesis has to be compatible with a longer time horizon.
If I understand it right, when we do have this quantum computer which we envision, it's not like everybody would have access to it, right? Those who want to have access to it will have to pay perhaps for the service of using that quantum computer. That's correct?
Well, you have to pay for a mobile phone, don't you? Right? You don't get things for free.
Is that problematic? Would that lead to even greater inequality, for instance? I mean, how do you envision, what are the cons to this?
I look at it this way. It is a very, very potent value creator, and therefore having to pay for a high value asset in the light of the values it could, think of again, a whole set of drugs for a disease that has not been tamed till yet. It's enormous, the potential. The advent of quantum computing in an era where cloud is pervasive is a very good way to democratize access. Right? Again, there are some challenges with data gravity and where you have the data, but in general, the technology behind making sure this isn't haves and have-nots is available today. We use it. The value part of it, whether it goes to everybody or not, really depends on whether they see value in it or not, whether they can derive value from it or not. And the transformative things that we believe, and we are seeing quantum computing now starting to deliver, that is going to drive a different value equation. And we believe in just looking at the history of high-performance compute, for instance, that when societies are benefited at this scale from in energy transitions to sustainability to pharma and health, that value will be shared and will flow down to every aspect of society.
Last word on this. Openness and engagement are the way we do this. Our community has driven very hard on making quantum computers available to the cloud, making software tools for performance management available to everybody on the cloud. The thing that will hurt us the most, that will lead to the greatest inequality in a really negative sense, is techno-nationalism. There's a difference between having national pride and wanting to invest in assets. That's a good thing. But when it comes to closing off your assets and preventing others from engaging with them, that's where we end up with the problem in this emerging technology.
Fascinating. We'll have to come back next year and assess where we are.
Yes.
Right? Raj, Michael, thank you so much for your thoughts today. Fascinating.
Thank you.